This is Steve. Welcome back to Smartest TV Day. So when I was in 11th grade, I made a video of me teaching the science behind tennis balls projectile motion with Steven. However, we only scratched the surface and we never dig deeper into the complicated equation that the internet showed me. So today I'll be teaching you the basics, teach you the complicated equations, and I'll show you the recent discovery that the internet made. Let's get started. This is my forehand demonstration. By having a close racket to the ground and making the swiping motion at the end, I was able to put my ball to the opposite court without making it go fly away. You can see the angled racket head in this picture, and this is the key factor of creating a topspin tennis forehand. This is the case where not enough spin was used and the ball went too high. This is my slice or backspin demonstration. When making a slice or a backspin, it's supposed to scratch the surface with 45 angle. In this case, the ball went high and it tilted the angle. Roughness of the surface of the spinning sphere creates a comparatively different air speed on the top and the bottom of the ball. The phenomenon creates two different air pressure as the air molecules get bunched up in the area where air travel at lower speed, which creates higher air pressure, and vice versa. The tendency of air to travel from higher pressure to lower pressure creates a force called Magnus force and is capable of shifting a sphere projectile's ordinary route. The usage can be seen in many net sports such as tennis, table tennis, and volleyball, and much more. In this case, the ball is going down. The explanation of the Magnus effect is based on the Bernoulli's principle, which states that an increase in the speed of a fluid occurs simultaneously with decrease in pressure or decrease in the fluid's potential energy. In this video, you can see the Bernoulli's principle as the ball adjusts itself to the center. As the ball is placed to the edge of the stream, there's more stream that goes around the ball and pushes the ball even more, and that makes the ball pushes itself back to the center in a higher force. So those principles allows the ball to stay in the center even though the stream is getting stronger or is getting slower. Isaac Newton was able to figure out this phenomena by watching a tennis game. He used his own principles, action and reaction, to figure out and define the phenomena. Wind in the bottom goes much more faster and it pushes the ball more than the wind top because the top goes slower. So wind that blows the bottom pushes the ball, and the ball itself pushes the wind back as action and reaction. So the ball goes downward. And the conclusion is the same, but the approach between Isaac Newton and the Magnus is different. This becomes this because of these. This is not that complicated as you think. I will explain to you very shortly. By looking at the first page, we can know a couple of things. The basics of physics, F, M, and A will be used, and we will be using trigonometry to find distances. In the first equation, F represents force, R represents density of air, B represents the radius of the ball, S represents the spin of the ball, V represents the velocity of the object. As the equation is written in multiplication, we can know that each variable is highly affects the outcome of force. By eliminating a couple of variables, we can conclude that there is a perpendicular force acting from the flow of direction, resulting in the flight path to be circular arc. Radius can be calculated by formula v squared over acceleration. And acceleration can be calculated by the equation F over mass. Reorganizing the original equation will give us R equals 3 times m times v over 16 times CL times R times S times b to the 3 power and pi to the 2 power. Here are some predictable outcomes. More spin of the object produces smaller r. Higher velocity will bring less curve. Objects with smaller mass, such as ping pong ball, will curve more. In high altitudes, the density of R will be lowered and result in larger radius. This is why some athletes are trained in the high altitudes. It is way harder to throw a curveball in the high altitudes. Conversely, golfers can hit farther in high altitudes. Using Pythagorean theorem, we can conclude that the distances is equal to yd equals r minus square root of r squared minus d squared. This video is from Australian YouTube channel called Vertesium, and this blew my mind when I first saw it. And he explains that it's way different than Bernoulli's effect or any other things that we saw before. As the stream contacts the ball, it pushes it up, but it also pushes the ball out, away from the stream. Once the ball is levitating, it remains stable because it drifts too far into the stream. That decreases the flow of water around the ball, reducing the force pushing it into the stream. And it drifts too far out, that increases the water flow over the ball, increasing the forces pushing it back into the stream. It makes the equilibrium position so stable, and any slight differences creates restoring force that moves the ball back to the equilibrium. It also gives angular momentum. For disc, it's very important because it has to maintain their vertical orientation.
This is a clear demonstration that is not just about the Bernoulli effect, right? It's due to the rotation of the disc that actually carries the water over and sprays it down, which pushes that back into the stream.